Hello everyone, my name is Psihoyos and I'm going to present you the work under the title A Modeling Framework for Fatigue Life Prediction of Selective Laser Melting Additive Manufactured Ti-6-4. This is the presentation outline. To begin with, selective laser melting is an additive manufacturing process in which the fabrication of parts with complex geometry from a digital model takes place by joining material in a layer-by-layer manner. At first, a powder layer is uniformly spread onto a substrate by a wiper, and then a moving laser heat source is utilized to selectively melt a layer of the powder AM metal alloy in a specific pattern. The powder particles melt and solidify to form a layer of the build part. Next, the platform moves down by the layer thickness, and the process is repeated again and again in a layer-by-layer manner until the entire part is fabricated. One of the major drawbacks regarding the wide adoption of the SLM process from the industry is the formation of process-induced defects or flaws. Defects can be attributed either to improper selection of process parameters or to instabilities occurring during the process. As it can be seen in Figure 2, lack of fusion defects formed in a metal AM part fabricated for optimized process conditions. The main categories of SLM defects are lack of fusion, keyhole, bowling, gas porosities, and surface roughness. Except from the surface roughness, all the other categories refer to internal defects, and these are of the main concern in the present study. The percentage and the distribution of defects cause high unreliability of properties and mechanical behavior of SLM parts. Especially, defects have deleterious effect on fatigue properties of AM metal materials because they act as local stress razors. The main goal of majority of research work is to limit the presented variability of defects in SLM parts. However, there is a need to integrate comprehensive methods in the analysis and design of SLM parts that account the effect of defects on parts fatigue performance. For this reason, in this work, a modeling framework for fatigue life estimation is presented. This framework accounts for the presence of defects in AM materials and can be potentially expanded in the design of SLM parts. The main assumption of this modeling approach is that fatigue failure is governed by the crack initiated from only one defect, which is known as the critical defect. The main sections of the presented modeling framework are thermal process simulation of the SLM part, which is performed in Thermal History Module of ANSYS Additive Suite, in which temperature and melt pool characteristics in part scale are estimated, and their processing determine the susceptible areas for defect formation. Based on the stress level of these areas, the critical defect can be determined. Then, a defect-based fatigue life prediction modeling is performed, which is based on an appropriate selection of a stress intensity factor. This modeling framework was used to predict the fatigue life of AM Ti-6-4 and its results compared with experimental data of the work by Du et al., which is presented here. In this experimental work, 9 groups of SLM Ti-6-4 hourglass specimens built with different process parameters, and all the specimens were polished to neglect the effect of surface roughness. Specimens of group 4 were selected in this work to predict their fatigue lives. The porosity of this group reached 1.2% of the nominal density of the specimen. Fatigue tests were performed at ratio -1, and the process parameters and the scan strategy are presented here. It should be noted that the present modeling framework can be extended to any AM material. As it was mentioned earlier, the thermal simulation of the SLM process for the fabrication of fatigue specimen was performed in Thermal History module of ANSYS Additive Suite. The main output of the simulation were the melt pool characteristics and the temperature fields of specimen in a layer-by-layer manner. In the first figure from the left, the 3D model of the hourglass fatigue specimen is presented, and in the second figure, the temperature fields of the specimen at the end of the SLM process can be shown. To characterize an area as susceptible for defect formation, an indicator is needed. The main indicator in this work are the melt pool characteristics or dimensions, as the melt pool is the fundamental physical feature that ensures the quality of a SLM part. If melt pool dimensions do not fulfill certain criteria about defect formation, defects are about to be generated. The main criteria used for melt pool characterization in this work are lack of fusion and keyhole criteria for defect formation. Lack of fusion criterion account for insufficient overlap of the successive melt pools, and keyhole criterion accounts for the melt pool mode of keyhole transition. As it can be seen, both of these criteria need some of the process parameters and the melt pool dimension. The melt pools in the gate's length region were examined. The main trending on all layers was that the melt pools located at the external surface of the specimen did not fulfill the lack of fusion criterion. This can be seen in these four figures of layers located in the gate's length region. The pink dots indicate melt pools which did not fulfill the lack of fusion criterion. For this reason, the surface areas of fatigue specimen can be characterized as susceptible areas for lack of fusion defect formation, something which agrees with experimental fractography observation, which showed that crack was initiated from surface-located defects. The critical defect location was identified on the surface of the thinnest cross-section of the specimen, where stress levels are the greatest. From this location, crack failure is likely to be initiated and propagated. Regarding the properties used in the fatigue life estimation model, as the defect size in SLM parts is less than 1 mm, the use of long fatigue crack growth properties may lead to overestimation of fatigue life prediction, as the plastic zone is not considerable and subsequently the crack closure effect is negligible. So, small fatigue crack growth properties must be considered. In this work, the available small fatigue crack growth properties of lengths Di64 from the open literature was used. Although lengths present some differences with the SLM process, the resulting microstructure is similar. Thus, length properties can be used in the fatigue life estimation model. The properties are presented in the Figure 7 and in the presented table. Figure 8 shows the model used in AFGROW for fatigue life estimation. AFGROW is a fracture and fatigue crack growth analysis software tool that provides many stress intensity factors used for fatigue life estimation. The selection of stress intensity factor was based on the location of the critical defect on the cross-section, and the most suitable model was the one for surface crack growth on solid cylinders. In the Figure 8, the presented model shows the perpendicular to loaded plane cross-section on which the crack is about to grow. The initial defect size was chosen 150 micrometers based from experimental observations. In the Figure 9, the comparison between experimental and predicted results are presented. As it can be seen, a very good correlation between the predicted and experimental results was achieved. The main limitation of fatigue life modeling was that the crack growth did not take place for stress levels lower than 200 megapascals, mainly due to the choice of initial defect size, which is the main limitation of the presented modeling approach. To sum up, the main conclusions of the presentation are: a modeling framework for defect-based fatigue life prediction of SLM Type-64 was presented. The main assumption of the modeling approach is that fatigue failure is governed by only one defect. At first, the susceptible areas for defect formation were predicted by processing multiple results from thermal history analysis performed in ANSYS additive suite, and from these areas, the most critical one was chosen, and it was assumed that failure crack will initiate from this defect location. Small fatigue crack growth properties must be considered as the effect of crack closure is negligible in defects found in SLM parts. Then, an appropriate stress intensity factor solution was selected in AFGROW fatigue crack growth analysis software to estimate fatigue life. The main limitation was that under a specific stress level, about 200 megapascal, crack growth did not take place, mainly due to the defect size. In future works, the effect of the defect size as well as the use of different case solution will be examined thoroughly. The expand of the current methodology in the design and fatigue life prediction of a realistic SLM part will be performed. This is the representative literature used in the present work. This is the end of the presentation. Thank you for your attention. For any question, you can send me an email in the present address.